Good morning, everyone. I'm pleased you're able to join us for today's Ask the Experts presentation, co-sponsored by Qualmark and our new partner, the Omnicon Group. I'm Cami Marsh, Qualmark's Global Marketing Manager, and I'll be your moderator today. Today's Ask the Experts broadcast is being recorded, and a link will be emailed to you following the live event. So should you wish to replay any portion of it, that presentation will be made available for you, and you can send it along and share it with your colleagues and cohorts. Questions can be submitted at any time during the broadcast by text using the chat screen, and we'll answer as many of those questions as time allows at the conclusion of the presentation. We're most pleased to be delivering to you today an incredibly valuable and informative presentation from two industry leaders that will demonstrate how you can leverage our expertise to create the most robust reliability program from design all the way through to production and beyond. Qualmark Center of Excellence is hosting today's presentation titled, Are Your Test Results Really Providing All That They Can? With our new partner, the Omnicon Group. Representing them is Mr. Nathaniel Ozarin, a senior reliability software engineer that has been with the company 15 years. He was named the IEEE Reliability Engineer of the Year for 2009 and has authored practical papers on FMEA and system area processing. Matt holds an MSEE from Polytechnic Institute of Brooklyn and an MBA from CW Post. We're most pleased to have him as a member of our expert panel today, and additionally, Qualmark's own senior applications engineer, Mr. Neil Dortenbaugh, will also be presenting. Neil holds a BSEE from Colorado State University and brings over 15 years of HALT expertise to the panel. So at this time, I would like to introduce Nat Ozarin to get the presentation started. And Nat, good morning, and take it away.
Good morning. Thank you, Cami. Good morning, everyone. I'm Nat Ozarin with the Omnicon Group. We're Qualmark's new partner, and we're very pleased with this arrangement. And since we are new to the partnership, I'd like to take a couple of minutes to tell you about us. We're an award-winning service company, engineering services company. We provide engineering services of all varieties to many customers throughout the world. And we're also a full product development company. We develop products from the ground up for many customers. We've been providing excellent engineering services internationally for over 30 years. And evidence of our success is in the fact that we have over 95% repeat business. Specialize in development of complete test solutions, which is relevant to the discussion because today's discussion is about tests, but we also developed test equipment of every sort for our customers. And along with that, we develop software for the full life cycle of electronic hardware, system and safety analysis. And for those of you who are facing the challenge of FAA certification, we provide full certification support services. And as reliability experts, we work with our customers to make sure that their products are reliable, safe, maintainable, and better. Here you see some of the disciplines and skill sets we provide to our customers. As an experienced engineering company, combine the experiences of all our engineering staff in these areas to meet a very wide variety of customer needs. And we hope to be doing this for the next 30 years. Now you've been introduced to Omnicon, so here's a quick summary of what we'll be talking about today. This presentation is based on a technical paper that was presented at a conference. The paper was a collection of practical advice for improving test reporting. And given the time limitations of today, we can only touch on pieces of it. But we hope that you would get a copy of the paper from Omnicon, and we'll talk about that later. Introduction to running tests and examining test results. Every software system, reliable software system, includes logic for error detection and reporting, but there are problems. And these are some of the problems you see highlighted here. Certainly, the more test capability and better reporting capability that you put into the system, the more it's going to help you find problems, monitor health, and come up with a better product in less time. But as you'd expect, the extra effort comes at a price. The question is, can you incorporate these improvements at a controlled price to get a better product in less time? The answer is, of course, yes. If you do it right, it will pay in the long run. Where are some of the applications where we use error processing? Here we have 6 kinds of areas that are checked. The first one, I/O data. Well, it goes without saying that when another system is sending your system data, you want to check it. But it's not sufficient to say that I've just gotten a bad parameter. You want to know what the parameter was, when it arrived, who sent it, and so forth. And same thing for commands. One system that we worked on, which was the origin of the paper, had 300 commands, 300 operator commands, and only half of them were valid at any one time, depending on system states. So when the system went into integration and people were trying to use it, they were getting all kinds of errors. But instead of jumping into the software to figure out where's the coding bug, the error report explained why the command was invalid, so people could see that it was not a software error, but rather a user error. And obviously, this would save you a tremendous amount of time during system integration. I'll mention just a third one, built-in test. There are many different ways to approach built-in test. The simplest, crudest way will tell you what you need to know as a bare minimum, but it's not going to help you bring your project to completion in the least time. And it's going to sometimes add to the headaches, because instead of giving you more helpful information, it sometimes gives you more confusing information. Improving error detection. How can you make something good better? Well, as I pointed out, putting in superior error detection and reporting takes time and it takes effort. And if you want to be thorough, it sometimes becomes more difficult than you would imagine. Because, for example, in some systems, occasional errors might be acceptable, and you don't want to report them. Sometimes data changes faster than it should, or sometimes data is not changing as fast as it should. That becomes a little bit more difficult to detect, but you certainly want to be aware of it. Data messages are a very common way of transferring information among software modules, but many systems don't check to see if a message is late, if it's redundant, if it's missing, or if one message is missing and may be acceptable. An occasional missing message may be acceptable. You want to have the right criteria to understand when a situation has occurred that it would be deemed a real error and you want to know about it. Health monitoring is an error reporting system where even after the system is developed, you want to observe how the system is doing to see if it's running in some kind of a degraded mode that might be acceptable, but also might reliably foretell of an impending failure. And health monitoring focuses on key performance indicators. These are the parameters that you want to track to monitor the system's health and determine whether or not health is deteriorating. This slide tries to condense an awful lot of the paper into one picture. The idea is to come up with software classes, pieces of software, modules, that are capable of doing the same thing over and over, but in different ways, with slightly different parameters. The first bullet says use a specialized class to handle each kind of error detection, such as rate of change. There may be a number of parameters flying around your system where you want to check rate of change. If it's time, you want to make sure that time is changing as it should be. If it's turn rate of a aircraft, you want to make sure that it doesn't turn too quickly, faster than the real airplane can turn. You know that would be erroneous information. So the idea to save time and to come up with a better way of detecting and reporting errors would be to find or develop a software class or module which is geared simply to check rates of change. Second bullet describes or summarizes a class that provides statistical processing. In many situations, a single error does not mean it's a real failure. Sometimes you may have to find 3 failures out of the previous 5 samples before you declare that something has truly failed, and that's the information that you want to report and log. The one system that we used had nearly 200 parameters, and most of them were processed statistically, either as 2 out of the past 4 failures would be deemed a true failure, or 3 out of 5. By developing one module that does this, that set up initiation time to check for 3 out of 5 or 2 out of 4, would allow you to handle hundreds of these things in our cases with the same piece of software. And as the third bullet summarizes, you want logic that does the same thing over and over again with a minimum of new development. And certainly you want to apply the key performance indicators to these processes, to the ones you particularly want to track and log. How to improve error reporting. I'll talk about just a couple here. Endless reports. Sometimes in your software, you put a capability to check for an error, and during development, that error happens all the time. And what happens is your monitor filled with these errors, your log gets filled up with these errors. What to do? The answer is to develop your test software using common modules, as we spoke about, to check only when an error first occurs, report it once. And a great improvement that's usually not done is to report if an error disappears. Sometimes through various circumstances, a reported error is no longer there. And you want to know that the error disappeared, because this tells you that there's an intermittent fault. Incomplete reports. Very common problem where one developer will put some data or information into an error report that nobody else understands. We used a piece of purchase software in our system where a cryptic error report came up with 5 digits in one word. No one had any idea why it came up or what it meant, and it took 3 of us a day to find out what was going on. So you want to take the extra effort to make sure that your error reports are as clear as possible. The bullet in the middle shows a typical error report, an imaginary error report that was based on a real system. Typically, during development in your monitors or in your log, the left side of the information is a timestamp, hours, minutes, seconds, the task or the module that reported the error, and then some free text that some software developer puts in. Well, the easiest thing to do is just have it spit out the text that you want, which typically wraps around the screen once or twice and makes it difficult to read. The example here in those 3 lines in the center is a sentence which explains what the problem was, what the possible causes are, and it doesn't wrap around the screen. It makes it very easy to read, and it makes it very easy for someone to troubleshoot what the problem is, or to determine that it's not even a problem. It may be an error caused by failure of some external system to do something. I did want to mention, though, the 4th bullet, reporting error reports by category. This allows users to filter out error reports that aren't of interest. We'll talk about that in another slide. Along with it, though, one of the bonuses in this extra reporting is to provide a basis for your decision whether or not to continue with errors during the highly accelerated stress tests. Typically, the rule is you want to continue, but in addition to simply getting an error report, you want to understand more deeply what the basis of the error was, so that later you can justify decisions to continue testing. Here you see 6 categories that were assigned to error reports in one particular project we worked on. The idea is that some error reports are way at the bottom level, such as level 1, that only a developer wants to know. Someone who's trying to maintain the system does not want to know about that. So by assigning categories to error reports and providing a capability to filter them, you come up with a much more useful system. Challenges. Well, you're putting in extra software to provide better error detection reporting. That software has to be tested. So it is going to add to your test time. High reliability software, particularly software that has to be FAA certified, may have as much as 25% of the content for error detection and reporting. And in order to get certification, you have to demonstrate that each of those lines of code works. And in some cases, or I should say in typical cases, although your goal is 100%, you'll never get there because some of the error detection looks for hardware failures. And unless you're willing to break something to test your software, which isn't practical, you'll never get to 100%. Your goal is to strive for 100%. You can reach as close to that as possible by doing all your black box tests on your complete system, and then backing up things that you can't test on the system level by results of unit tests that were done on the bench. So yes, it costs more and it takes more effort, but it gives you an improved reliability and maintainability capability that would be useful for the life of the product. Costs and benefits. Well, I've been talking about that saying repeatedly that by putting the extra effort in, it pays in the long run. But I can give one example from one complex project we developed. The people who were integrating the system were not the software developers. And in the system with 300 operator commands, only half of which were valid at any one time, the integrators were getting endless errors. But they could see that most of the errors that they saw were operator errors. They were trying to exercise a command, for example, at a time when the system was not in the right state for it. So instead of going back, I should say, instead of writing error reports and then sending them back to the software developers, people could see very readily what was an operator error and what required further investigation. So integration time was slashed by having better error reporting, explaining in full sentences what the problem was and why it was reported. this concludes part one. This was Omnicon's talk about development of improved error reporting and processing. The next part, presentation, describes accelerated stress testing, limit testing to further improve the reliability of the product by finding early errors and finding the weakest parts of your design. So the question is how to approach and benefit from the accelerated environmental stress screening and limit testing. So this concludes my portion. Thank you.
And thank you, Nat. This is Neil Dortenbaugh with Qualmark, and I'm really excited about what we're learning as we work with our new partner here, because we're really talking the same thing from different angles, and the value of using both is significant. I wanted to start off with just a basic description. I suspect that most of the people who are logged in have used HALT and HAS or accelerated ESS limit testing. But if you haven't, I wanted to go through a brief description of what it's about. And there's a lot of different definitions out there of what this testing is. So as I talk about it, you'll have an idea of what it is I'm talking about. If you think about screens, environmental stress screening in production, burn-in is the one that most people think of. Back in the 70s and 80s, it was helpful because we hadn't learned how to build ICs yet. But nowadays, people find more and more that a simple burn-in doesn't catch what they need to find. Thermal cycling will find more things because we'll not only find those that are accelerated by high temperature, but also by low temperature and by thermal change. So we're able to capture more defects in less time. And if you accelerate that thermal cycling by doing the change rates very quickly, far beyond what the unit would normally experience, then you're able to uncover even more. That's particularly valuable for solder issues because the accelerated thermal cycling will accelerate solder creep and bring out bad solder joints very quickly. If you can get vibration and combine it with those others, that's really when we're talking about HAS, a highly accelerated stress screen, then you're able to capture even more of your failure modes. Based on what we have seen as failures in our labs and the research that we've done, we have found that the failure modes that are latent in a product before it's ready to be shipped are detected by or brought out by a range of stresses. You can see that a simple hot dwell is only a fraction of the total stresses. The thermal ramping will find another 10%. Cold dwells are valuable as well. And vibration, we're finding 20% of the failures in vibe alone. But when we get into a final combined environment where we're doing rapid thermal dwells and vibration, we're finding that's the single most effective stress for driving out latent failures. Now, the trick is that normally things like high ramp rates, high vibration limits, combined stresses aren't defined for an ESS profile, and you haven't designed those, obviously. So you may not know the best stress levels to use for an effective and safe environmental stress screen. Limit testing is the key to that, and that is what we often we call HALT. That will identify the true absolute limits for a design by pushing until failures are found. And once you finish that, you can use more stresses and higher stress levels in your screens in order to make those screens happen faster and be more effective. And when you do that on a product before release and to wring out the product, and find out what the weakest spots are in the design, then you'll have a product that at launch is more mature and less likely to stumble out of the gate as a new product because you found those things. So we'll talk a little bit about the process of limit testing, mainly because I want to show you how valuable the software failure detection that has been described by Nat fits into the limit testing. Because limit testing really is a failure-oriented test. Our goal is not to pass. You never pass this test. The goal is to find out at what points it fails and how it fails, and do an analysis of the failures. Having software in place that will help you understand those failures, catch them when they happen, and identify them for you is extremely valuable. You take the corrective action then, and in the end have a product that you've eliminated design weaknesses in, and you have a clear understanding of those operational and destruct limits. You've reduced the residual risk that is left behind for failure in a product by identifying possible sources of failure and eliminating them before you've released the product. It's a fairly straightforward test process. We will expose the product first to thermal step stressing, going through cold, then hot. These are actually ordered from least destructive to most destructive so that we can get the most possible out of the samples. Once we understand the limits cold and hot, we'll go into a rapid thermal transition, changing temperature as fast as the chamber will allow. If we're testing at board level, we'll typically see 60 to 70 degrees C per minute changes on the product. If we have a full up unit, we can usually get the inside to change at around 30 degrees C per minute. Then we move into a vibration step stress at ambient temperature, find what fails first in vibration or second or third, and then a final combined environment where we step the vibration up while we're doing the rapid temperature cycling. And it's a cyclical process that we go through. First, apply a stress, increase that stress until you see a failure, determine is it a hard failure or a soft failure. We call it an operating limit or a destruct limit. Do some analysis on it, find out a root cause. Often at this point, we're trying to determine a workaround or some way to continue testing. This is where the ability to identify and choose to ignore a failure being reported by software is extremely valuable. If I can keep testing and let one particular function not work, then I'll learn even more. Make some improvements, do the corrective action, do the workaround if necessary, and then take a look. Have I learned all I can? Have I reached the limit of a particular stress where if I apply any more, I'm not going to get valuable failure modes? The trick is to get failure modes you can learn from. And if I'm not learning from the failure modes anymore, I'll switch to another another stress level or another stress type. So if I haven't hit maximum robustness yet, found out everything I can, then I'll keep going, stepping through all of the stresses, increasing the stresses in a stepwise fashion so that everything I'm finding is information about the weakest parts of the design. Once I get through with that, I've learned everything I can about the product, improved it as much as I can. Now I know what I can do for my accelerated stress screening or HAS limits, and I can develop a profile for that and fixturing as necessary for vibrating the product in the system. Move on to demonstrating that the screen and fixture are effective. There's a process for that that's very well defined. And then get that launched into production. At all points through here, we are looking for failure modes. So any information from functional test software on what types of failures we're dealing with is invaluable. So I'll just touch one more time on the things that I always like to say 3 or 4 times because they're so important. Keep in mind that the testing we're talking about is failure-oriented. It's a discovery process. It's almost an error to call it a test. It happens, if you're doing it before the product is released, it happens very early in the design cycle so that you're learning as early as you can what kind of failures your product can exhibit. It is very important that the product is monitored and functionally tested when the stresses are applied. It's never a question of stress it, take it out, and see if it still works, because you miss transient failures that only occur under stress and later turn into NDF problems in the field. That monitoring is obviously where the software links in. And once you finish that limit testing, you also will have confidence that what your product can truly tolerate, so you can expand the stresses, increase the stresses that you use in reliability demonstration testing or other life testing, so that you can get it done more quickly by using higher stress levels than you normally would, because you understand your product so thoroughly. And one last thing to consider, and the last important piece of what this process is the idea that we are not trying to simulate an intended use environment. We're trying to stimulate failures quickly. And that requires a different set of stresses. A product that will never see extreme temperatures is still subjected to those temperatures in this testing, because that will very rapidly show us the failure modes. Same thing with rates of change and the repetitive shock vibration that's used in the testing. It is an aggressive, fatiguing method that lets us very quickly see the weakest parts in the design mechanically. So with that said, let me go on and talk a little bit about the true practical value of having good functional test software in place when you're doing your limit testing, as well as during your screening. The value of the limit testing is in the failures. That's the nuggets of gold that you get out of doing a test. If you have a failure and don't detect it, then you've thrown away that nugget. An undetected failure is a waste of time and money. So your system needs to be able to identify failures in order to let you really see what's going on. And there's a rather sad and interesting trend that I have noticed. We have a lab here at the Qualmark headquarters, and I do a lot of the testing here for customers. And more, the customer is fighting with their functional test and not doing the testing that we want to do, because the software is being faced with hardware doing stuff it's never done before. And so they're on the phone back to software engineers trying to understand what the heck's going on, with screens of error message streaming across in front of them, and trying to figure out what's going on, because the software isn't being helpful in the process. And it links into something that we've always talked about when we talk about HALT and limit testing. You want to start it early in the design process, but you don't want to be troubled with failures that are purely due to the fact that your design is a prototype and it's not quite finished yet. Those are failures that have no value. The same thing applies in your software. If you have immature software, or in particular software that has incomplete or sometimes non-existent error handling, it can really slow you down when you get into limit testing. I think that it is simply human nature and the force of timelines and all the rest that make software engineers focus on making it work and not focus on handling errors in an intelligent way. And I'm sure that we have all dealt with the fact that even our friends at Microsoft tend to cut corners when it comes time to reporting errors. And something fails and they give you a very polite error message that tells you absolutely nothing. And error messages like that, or worse yet, system shutdowns, will dramatically limit what you can get out of a limit test. And as I have watched people wrestle with the functional test software and problems with it in the HALT environment, I've found some specific things we'll recommend to people. When people are coming into our lab, it's not uncommon to have them call up and push out, say, oh, we can't come in next week after all. There's two reasons for that. Number one reason is I can't get my samples because somebody found out you're going to break them and they don't want to give them to you. But the other thing is I'm not done with my functional test software yet because they've figured out that there's changes that need to be made, things that need to be in place in order to properly report the errors. If you're planning from the beginning or working with a company like Omnicon to get the error reporting software in place early, then those delays can be avoided. And some of the key things when you're doing, you're talking about the functional test software, and this is all stuff that Nat, or most of it is stuff that Nat has talked about. For one, never deliberately shut down. And one of those key problems that pops up is over temperature conditions. Software will routinely have limits in place, and often, if it thinks it's overheating, it will turn itself off. We need to be sure that that's not the case in the software that you're using during limit testing. We intend to blow right past those specs and see how it really fails. So certainly report it, certainly log it, understand that it's there, have the ability to ignore it or condense the information rather than having your screen flooded with information about temperature failures, but don't shut it down. And a thing that, as I say, we're making the software see the hardware doing things it's never done before. So it's not unusual to be on the phone with the software guys making changes, and you want to be able to load new code into your unit while you're in the lab. So that ability needs to be in place. If you're doing the testing in your own facility, even then, you want to be able to very quickly get new code into your system. And another thing is, of course, logging is important, but in safe places. I have worked with a customer who is very reluctant to take his unit to failure because if it failed and shut down in a certain way, he'd lose the logs because they were being stored on the unit under test. People like Omnicon are smart enough to know that we need to put those in safe places and have them duplicated so that you can have access to that valuable error information even after the unit under test has gone south. I wanted to talk a little bit more about KPIs. The key performance indicators are very valuable from a prognostic standpoint in manufacturing, and having test software that will keep track of those is quite valuable. It's also very valuable in HALT, in that limit testing, because it gives you the chance to tie the key performance indicator to a true hard failure. Now, before a failure becomes detectable, there may be those shifts in performance that indicate an impending problem. Typically, as Nate has described, systems will have failure modes that they will allow to exist 2 times out of 5. If you've ever done testing on hard drives, it's extremely frustrating because there's about 8 layers of code between you and the hard drive that are doing everything they can to conceal failures on the hard drive and cover up for them and take care of them so that you're not bothered by them. But those can turn out to be very valuable indicators that a particular system is weak. You'll make your testing more effective and your screening more effective if you understand the key performance indicators. It basically tightens the net on your production screen so that you don't have to have a hard failure in order to detect a unit that is marginal. You can look at its key performance indicators and say, yeah, this one's still passing, but it was struggling to pass. There's something going on here. And if you've got the functional test software in place to catch that, you will catch it in production, and thanks to the information you learned when you were doing your limit testing, you'll know if that's an indication of a product that's going to possibly fail early. And I have some examples of the value of key performance indicators. In this case, we were testing hard drives, and we were looking at thermal performance. And the first graph you'll see is our performance indicator is input outputs per second. That's one that kind of gets past some of those screening efforts, because anytime a drive is having trouble getting information, it takes a little longer to get the data to you. So you can use input outputs per second as a performance indicator. And what we found was that systems with early performance degradation in input output per second were the ones that actually stopped transferring data first. So when we were able to, in this case, we were comparing two different lots of drives, looking to see if one was compromised compared to the other. We're looking at IOs per second here, so higher is better. And as we moved up in temperature, down in temperature, this is cold, you can see we're doing minus 20, minus 30, minus 40, far below spec, but one particular lot is showing better performance than the other lot was showing. So at those temperatures, lot 2 is showing more problems. And in the end, lot 2 showed earlier hard failures as well. We can do the same. We can also look at error rate as we went cold and use that as a performance indicator. It was a great indicator and would certainly be something that you'd want to bring into a accelerated ESS to highlight a potential problem drive. If I'm getting, I'm still working fine, I'm just getting more errors trying to get there, even though I'm way below spec, I am learning that this lot has problems. And if that was a single drive of 1,000, that drive's got a problem that has been demonstrated to indicate potential for early failure. When we went hot, we found even more dramatic indications of this. Hot is always bad for drives. It's difficult for them to function as they get hotter. All the head flight characteristics start changing and everything gets tough. But as you can see, the unit that we were testing from lot 2 was showing a huge error rate very early in the hot temperature stepping. Lot 1 moved on, stayed really until we started hitting limit of the technology there, and it began to throw more errors. So this is the kind of information you can get if you're tracking that KPI's data, storing it, and using it in production. And I would like to wrap up with a quick case study from a white paper written by Allied Telesyn. This paper came out, I believe it was in 2005. And they have a facility in New Zealand, and they were doing communications equipment. And during HALT, before they'd released the product, they were saying, you know what, we're finding a lot of software failures in HALT. It all links in, and if you actually begin a debug process on your software as you're forcing it to deal with your hardware doing all this unusual stuff. There were changes in the hardware caused by the stresses that caused the software to malfunction. with the proper stuff in place, the proper software in place to report that, you'll be okay. And this is what they found. When they were looking at failures, 70% of their failures in HALT were hardware related, but 28% were software. So they're finding software bugs. It's an effective place to find software bugs. And if you have that failure reporting in place, you can debug those much more quickly. And oddly enough, most of those software failures were detected in the thermal part of the test. The vibration is more of a mechanical stress. It's forcing mechanical failures, so you're dealing more with cracked components and things like that. But cold, hot, and rapid transitions are really simulating the effect of stack-ups in parameter variations and things like that that can cause inputs to do weird things and make the software deal with things it hasn't dealt with before. So just an idea of some of the problems they were having. Of course, systems crashing and the rest, power-up sequencing screwing up. If you've got things like systems crashing and silent reboots, those are indications that your functional test software isn't giving you enough information, or you haven't prepared the software well enough for the fact that it's in HALT. Crash is one of the worst things that can happen because you use a lot of information. You lose a lot of information when that happens. But the final statement from Allied Telesyn said that it's essential to have monitoring and test suites that uncover more than just hardware faults. You want to be tracking what your software is doing so that you can understand what's happening there. And it proved to be very valuable to Allied to do that work. So the basic summary from that is intelligent, complete, and rugged functional test software will make all of the testing that you're doing in access and limit testing, HALT and HAST, where you're doing failure-oriented testing, all that will be faster, easier, and more valuable with the right type of functional test software in place. And that concludes my portion of the presentation and the presentation in general. So if there are questions, I'll turn things back over to you, Cammie.
Yeah, we have a few questions here, and so I'll just go through them one at a time, and between yourself and Matt, you can respond to them accordingly. So the first we have, you said the presentation was based on a paper. Is it available? I believe that was directed towards Matt.
Yeah, the paper is available. I would suggest anyone interested in the paper to log on to www.omnicongroup.com, and one of the tabs or links there will take you to available papers, and the paper can be downloaded. I would suggest anyone who has more than a casual interest in the topic to do so, because the paper is a collection of practical, real-world suggestions with actual examples, and it could be very helpful in developing your own systems that way.
Okay, and the next we have here is how to handle error reporting when an intermittent error is reported constantly. That is, how would you prevent the nonstop reporting from hogging the logger?
I talked about that briefly in terms of reporting only when something first fails and then reporting just once when it heals. But sometimes an intermittent will be rattling on and off constantly. And for a situation like that, and we've experienced problems like that, the one way to handle it would be to not report an error except every, say, 1 minute or 5 minutes or 10 minutes. You can count the number of errors, and then at the end of 10 minutes, simply report that 55 errors have been found in the past 10 minutes. That way you would get one report every 10 minutes, and it would not clog your logging system.
And this is Neil again, I'll also toss in that that's an extremely important piece in HALT because intermittents are quite common. As you're stepping up, you'll hit a stress where something is just starting to happen and it'll be a little bit of a problem in one unit. Then at the next step, it's a constant problem in one unit and an intermittent problem in another. So being able to detect, deal with, and not be distracted too much by intermittent issues is important.
Okay, thank you. Another, would power-up error processing / reporting be different from operational error processing reporting?
I'm going to ask you to please reread that.
Would power-up error processing or reporting be different from operational error processing or reporting?
Okay, understood. The main difference between power-on checks that most systems do when you first start them up and background checks, which the system does when it's normally operating, is that you want to capture any problems that you found during power-up permanently. An error that occurs and then heals itself during operation may be lost, but certainly if something occurs during power-up, you want to capture that permanently and not permit it to go away. That's the essential difference, I think. But you would still be wanting to check the same kinds of things. That's it.
Okay, thank you. And Neil, I think I have one more for you. Can you reiterate the difference between limit testing and HALT?
That's a good question. You know, we a lot of times we talk about just HALT and HAS, but what we have found is those specific narrow definitions don't do a good job of describing all the ways that people use this technology and this test method. And there are ways to accelerate your stress screen that aren't exactly HAS, and there are ways to understand what the limits are to your product and improve the product that aren't exactly what we define as HALT. So HALT is, I guess the limit testing is kind of a subset of HALT. It implies more a goal of identifying limits rather than a goal of design improvement on a new product. Limit testing would be something you do to get into an accelerated screen quickly rather than debugging all the problems in a new design. But they're thought of the same way. The processes are the same. One is a subset of the other.
Okay,
and
thank
I'll
you.
also,
Uh-huh.
I was just going to touch back to the question of power-up diagnostics. That also hits home when you're doing limit testing, because one of the most valuable things you can do as part of your functional test in limit testing is do a power cycle, because there's a lot of things that happen during power cycle that don't happen at any other time, like power supplies coming up in an orderly fashion. So just having your system running continuously isn't as valuable as shutting it completely down and making it come completely up. And any failures that happen during that power-up process but don't happen again once it's up and running need to be captured and understood as well. So from a HALT standpoint, it's good to have that power-up failure information.
Okay, thank you very much, Neil, and then especially to Nat and the Omnicon group for taking time out of your busy schedule to present today and kick off our exciting new partnership. I would like to remind everyone that the Omnicon group offers a full range of engineering solutions from the earliest of design stages all the way through to production, and that in tandem with Qualmark's accelerated life testing and limit testing can help you achieve high-quality, robust products with the most long-term cost savings. If you'd like to speak with Nat, you can be reached.
Cammie, I see one more question that's popped up.
Oh, sorry, yes. Let's capture that before we sign off here. It says, how do you determine key performance indicators, KPIs?
Yeah, and I think Nat and I both might have some ideas on which ones are the best ones to use. In general, if you have a system that, if 2 out of 5 failures are okay, what might be an indicator that that failure is going to happen, or actually that failure happening 2 times out of 5 is a performance indicator. Nat, do you have anything to put in on that, the best way to determine what to track for key performance indicators?
I viewed the question in kind of a different slant. I read the question as, how do you determine which parameters to monitor? Which parameters are the key performance indicators? And there, I guess you would have to go back to your understanding of system operations to figure what is essential for a system to operate successfully. Which parameters would be most telling as an indication that there may be health issues or impending problems coming up? And in that case, it becomes a systems engineering analysis. And those are the parameters, once you've determined them, those are the ones that you want to track most carefully. That would be my 2 cents on the question.
Back to the design engineers and an understanding of what's happening in the hardware and or software processes and what it makes sense to watch. And then certainly watch those closely as you're doing your limit testing to confirm that they are indicators of impending failure.
Okay. Well, thank you, and it looks like that wraps up the questions that we've received. As I was stating before, should you have any additional questions or have other topics that you'd like to go over with Nat or with Neil, you can reach Nat at Ozarin, Ozarin, at omnicongroup.com, or just send Qualmark an email at marketing@qualmark.com, and I'll certainly put you in touch. So thank you, everybody, for attending Qualmark's Ask the Expert presentation today, and please visit our events page on the website often to keep abreast of all the upcoming free webinars that we host. There's good material, and we always welcome as many attendees as are available and interested. So thank you for joining us today, and we look forward to having you again. And thank you, presenters.